system.
Sorry, I forgot to hit record. Sorry, carry on.
So let's have a little look at, well, let's just remind ourselves first of all. So this might be familiar from the introduction session. So when we're looking at a graph, what are we looking at? Well, a graph is composed of two key elements. The first is the vertices, otherwise more commonly known as nodes, and they are the dots here. These are your entities, your individual discrete units, hence this coming from discrete mathematics. And the other component are the edges, and these are the links between the vertices. The general notation that is used is when listing the vertices in a graph, we use V1, V2, V3, and so on. This means that edges can be described using their vertices. So we get these pairs of vertices, and they enable us to be able to describe an edge. So a link between V1 here and V2, that will be described as V1, V2. And this just makes it neat and tidy to be able to describe the graph in this kind of coordinate-based fashion. And edges can also be described on their own and normally using the common notation of E1, E2, E3, etc. So that's it. Graphs are simple. You know, this is a very simple way to start abstracting complex information. So there's a few little kind of bits of nomenclature that you get that, so edges that have the same end vertices are parallel. So here we can see an example that E1 here, this edge between V1 and V2, is parallel to edge E2 because they share vertex 2 here, V2, as their common ending edge, their ending vertices. An edge which has the same vertices as its beginning, as its start and its end, is a loop or a self loop. And so we can see an example of that here with V5, where edge 3 here is a self loop. It just loops back on itself. Edges are said to be adjacent when they share a common vertex. So in the same way that edges become parallel, they're also adjacent here in, for example, E1 is adjacent to E2, as E2 is adjacent to E4. Two vertices are adjacent if they're connected by an edge. So here V1 and V2 are adjacent vertices because they're connected by E1, and V2 and V5 are adjacent because they're connected by edge E2. So this really is the very the whole basis of networks and graph theory. So let's have a little look at the first problem. This is what Euler developed graph theory originally for. This was kind of his first test kind of toy problem in a way. So in Königsberg, there is this setup in the city where there are bridges crossing the river, and it was a very fashionable thing to do, to go out and take a walk around on through the city and tour across these bridges. But what they wanted to know is what the optimal route was to walk across these bridges where you cross each bridge only once. Is that possible? They didn't want to repeat themselves and go walking backwards and forwards across the same bridge, but they wanted to tour around and just walk across each bridge only once. So let's have a go. I'm going to give you just a few minutes, just sit on your own, and can you plan a walk across these bridges where you cross each bridge only once? And beyond that, can you represent this problem as a graph? So as a set of vertices and edges. And so, yeah, try and draw this as a graph representation of the problem and see if it is possible to plan a walk where you cross each bridge only once. And we'll come back in just give you 3 minutes just to have a little go at this, and we'll come back and we'll put in the chat, see how everybody's done. So you probably want that. Okay, so let's see how you got on with Euler's bridge problem. Perhaps just put in the chat whether you think it's possible or not to cross each bridge, plan a walk where you cross each bridge only once. We got quite a consensus here that it is no. So, and this is exactly what Euler found. Dan's building bridges. That's, I was thinking outside the box. So, yeah, this is the representation that Euler came up with of this bridge problem. He was representing here the paths across the bridges as edges and using the points on the islands and the banks as the vertices or nodes. And here, yeah, he found that with an even number of vertices and an odd number of edges, it was not possible to plan what is called a unique walk across the along the edges. And this actually became the proof for this concept, that actually you need an odd number of vertices in order to be able to plan a unique walk between all of those points, covering all of the edges in a complete graph. And this is what's spurned forward the area of graph theory and has built into what we now know as graph theory and network analysis. So it's this idea of being able to take what is, a real world problem, abstract it, and then solve it mathematically. So that was kind of the first graph theory problem. And then people went on to explore this realm of graph theory. And this meant covering in maths, because you've got to be pretty, you've got to make sure you cover all the different bases. They wanted to look at, well, what are all the different types of graphs that we can have? And so you get things like an empty graph, where we have only vertices and no edges. You get a null graph, where there are no vertices at all. But for completeness, maths and graph theory like to include these kind of concepts. A trivial graph is one that only has one vertex. And a complete graph is like we saw with Euler's 7 bridges problem. It's where all of the vertices are connected by edges, and each is connected to another. So going a little bit further from those kind of very simple base descriptions of what a graph can be, we get a variety, a whole lot more graph types, and that we get what are called undirected graphs. And undirected graphs are where the direction of travel between the nodes or vertices doesn't matter. They're just a link. Then you get directed graphs, where they are, where direction does matter. So from node G to node F is different to node F to node G. And yeah, just direction becomes important. And quite often we want to be able to use directed graphs when working with healthcare data in order to be able to show this direction of travel between whatever our entities are, whether people or often services teams, and explaining those connections. Then we get things, some slight twists on these two, directed and undirected graphs. We get things called signed graphs, where it is a simple dictonymous description of the edges, where they are either positive or negative. You then get multi-graphs, where you can have different types of edges. And so, for example, we see here, this particular example shows that we're using different colored edges to represent different relationships between individuals, whether they're family, a friend, a co-worker, or a neighbor. Then we get weighted graphs, and these are a more common type of graph that we use, where the weight represents the amount of activity along an edge. So in the case of mapping services into healthcare services into a network, it might be the number of patients being referred from one service to another that is represented as the weight of an edge. So this is not a complete list of all the different graph types. It's one of those that if you can think of it and describe it, you can build it into a graph. But these are the most common types of graph that are used, and these, you'll have noticed, actually have a bit of code with them, and these are how these different types of graphs are described in Network X, which is the one of the pieces of network analysis software that we use in Python. So we've got our graphs, we know how to build our graphs up, and we can have them representing different things. We can weights on our edges, we can put direction in, and we can abstract the world into this graph, which is great. But then what can we understand about our graph? You know, what more can we get from it? So this is where we get into using graph metrics, and these are measures of the graph, whether it be at the network level, so at the whole network, the whole graph, and describing the structure of the graph as a whole, or at the node level, where we're just saying things about individual nodes in the graph and distinguishing between them. So at the network level, the common kinds of descriptions that we use are things like simply the number of nodes and edges. And this gives an idea of both the network size and its complexity as well. So, you know, a graph that has a network that has 5 nodes and 3 edges is a much less complex graph than one with 200 nodes and 60 edges. Then we get this idea of density, and this is to do with the number of links in relation to the number of possible links across the graph, or the number of edges. And this is given normally as a number between 0 and 1, where 0 is what we saw as an empty graph, and then all the way up to a complete graph, which has a value of 1. Then we get onto this concept of degree. Now, degree is all about the number of edges intercepting any given node. And so each node might have, one node might have 2 edges connected to it, another might have 5, another might have 6. And you calculate this for all of the nodes, calculating their degree, and then take an average of that across the graph. And that gives us an idea of the level of connectivity within the graph. Building on this idea of connectedness of the graph, we get this concept of modularity as well. So this is about how many nodes are linked together closely, and we start looking at grouping here with modularity, that you get nodes with high levels of connectedness and those that are less connected that sit on the periphery of the graph. And yeah, this modularity is a particular metric that can be calculated and then mapped onto the graph to be able to show visually this level of connectedness across the graph. Then at the node level, now I mentioned about directed graphs. When we have a directed graph, we can have 2 different types of degree measure. We can have in degree, which are edges that are coming into a node, and out degree, which are edges going from a node. And then this is overall just known as the degree of the node. So we can add in degree and out degree together to get degree if we got a directed graph, or we simply use degree if it's an undirected graph. And so in this way, we can start to differentiate again between nodes and seeing which nodes are more connected than others. And when it comes to understanding this in relation to healthcare services or social networks, people, those with a higher degree are those that are connected more within the graph, within the network, and so connected to more services, connected to more people. Then we get this individual measure of node modularity, and we get how connected a particular node is within the graph and in relation to other nodes close to it within the graph. And then an important measure of connectedness within the graph is this idea of eigenvector centrality. And this is whereas modularity looks at nodes that are close together, eigenvector centrality looks at the connectedness of a node across the whole graph, across the whole network. And it's this connectedness and its ability to facilitate connections between other nodes within the network. These are all quite abstract, well, relatively abstract concepts, and there's a whole lot of maths that sits behind them. Thankfully, when we're actually using these in practice, it's more about understanding the concepts rather than the maths that's sitting behind this, because thankfully there's built-in functions in Python for us to be able to calculate modularity, eigenvector centrality, etc. So going even further, these are the most kind of common and kind of the types of metrics that you start out with looking at on any graph. We can then go on to some more complex measures of a graph and start looking at things such as there are approximation and heuristical techniques to look at connectivity across the graph. And quite a lot of graph metrics are concerned with different ways of measuring connectivity across the graph. The other ones that go on to are looking at cliques. So this is where you start looking at how well nodes group together and whether they form specific clusters, and whether you get separate cliques within a graph that sit separate to the main graph, or whether there are some that they are only connected by a single edge. And these are called cliques. They sit separately or more distant from the rest of the graph. Then we get clustering approaches, which is where looking at how well nodes again group together, but not looking so much at this distance, but more about how not identifying those that are far apart, but those that are close together, and how well they start grouping together. Interestingly, when I've applied clustering techniques, looking at healthcare service data as a network graph, it's interesting to see how they cluster together commonly by geography is the main way. And you see really quite a distinct separation in the geography of services using clustering techniques. Then we get these measures of centrality as well. So this is where we got things like we can look at degree centrality. So which nodes are most highly connected in terms of their numbers of connections. Eigenvector centrality when they're facilitating connections across the network. And cat centrality, which is a variant of eigenvector centrality that's just calculated in a bit of a different way, but is also, again, it's an alternative measure to eigenvector centrality. Another type is communities, where we can look at again, how well, this is a different way of looking at how nodes group together, and that it will just try and find the closest matches, the shortest paths between different groups of nodes. But these approaches of cliques, clustering, and communities all have slightly subtly different. Then we get these ideas of isolates, and isolate is within your graph, there is nodes that might not be connected to the rest of the graph, and these are referred to as isolates. Then we can do things around link analysis. So this is looking at possible connections that could be formed between nodes. If what are the most likely connections that could form, starting to look at this kind of predictive element, given the closeness of nodes to each other and nearby connections. Then we get shortest paths. So this is how do you, is similar to the Euler's bridge problem, that you're looking at what is the shortest path between two nodes, and which edges and nodes should you traverse. And so we can calculate within a graph, for example, and any graph, the shortest path between any two nodes. Then we get similarity measures as well, and these are really interesting for looking at change in network structure over time. So in my work, I use networks for modeling large healthcare systems, and I'm interested in how that system is changing and the structure and operation of that system is changing over time. And we can use similarity measures to look at how the overall structure and size of the network is changing from one time period to another and compare them. So the Python package that I find by far and away the best for conducting network analysis and actually calculating graph metrics is the NetworkX package. And I've just supplied a link to the reference material, the documentation that has all of these different algorithms listed out, goes into all of the maths behind them if you fancy having a read. And yeah, there's lots and lots of information, different algorithms. I mean, I've only kind of hinted here at some of the different types. But what we're going to do is just go through a little bit more about these different metrics. So hopefully this actually is kind of a first stop in some ways if you're doing network analysis and you want to have a little bit of a reference about what a particular metric is, how it's used, and the function in NetworkX for applying that, and what you actually get returned. So yeah, start with a nice easy one here, that is degree. So the number of edges intersecting a vertex. And in an undirected graph, we just got the single degree value. But in a directed graph, each vertex has got an in degree and an out degree. And we can add those together to get its total degree. So yeah, the degree being this measure, an indicator of system complexity. And at the nearest neighbor level. So this is a term that's used in graph theory when we're looking at the immediate connections between nodes, and nearest neighbor is exactly that. It's those that are immediately beside a particular node, those that are closest within the graph. And in operational modeling, we can understand degree as the number of interfaces a service has with other services. So we can start to see which services are actually interfacing with more teams, or those that only perhaps interface with one or two teams. And so if you're looking to make changes in your system where you want either a team to connect with more teams or to actually slim down what it's doing and have a more discrete, refined, simple pathway. So you want to reduce the number of interfaces with other teams. You can measure change in degree over time and look and see if the changes you might be making in the real world are actually having this change in how that particular service is functioning. And so when degree is implemented, it's done using the degree function. And all you have to do is pass your graph object into the function, and if there's a weight component to this, if it's a weighted graph, then you can add that as well. So you can define mbunch here is an argument that allows you to say, oh, I just want you to return the degree for a particular subset of nodes. Or if mbunch isn't used, then it returns degree for all of the nodes. So modularity, this is a measure of the structure of the network. It measures how well the network divides into modules with many connections within a module and fewer connections between modules. So again, it's this kind of grouping. And this is where we can see whether connections are being equally distributed through the system or irregularly. And it's an indicator. It's often used before going on to do clustering and community detection within a network, just to see whether it's appropriate. Because, as we'll come on to in a minute, when we get onto looking at clustering and community detection, these can, in larger networks, these can become what are called NP-hard problems. That are solved using heuristical approaches and approximation approaches, because you can't run all the different possibilities. It would just take too much time and too much computational power. So modularity is a simpler mathematical indicator of grouping and clustering and communities. So it's kind of the first one that you'd normally run. And we can do this for an undirected graph using modularity matrix function, or if it's a directed graph, it's a directed modularity matrix function. So density, this is where we're describing the completeness of the graph in terms of the numbers of possible connections and actual connections. And so network density is literally actual connections over potential connections. So a simple proportion. And so this is whether you have highly connected, gives you a measure of a single figure to describe how highly connected or sparsely connected your system is. So yeah, if we're aiming to connect everybody, then you want to see high density. But if you want very distinct pathways within your system with minimal crossover, you'd be looking for a lower density value. And again, this is why Network X is fantastic. We can just pass our graph object in and to the density function, and it will return the density value for us. So cliques. So the technical side of this is that cliques are formed by removing edges around a node until a graph, in a graph, until the subgraph becomes complete. And is just one strategy for community identification and clustering. And so what we've got here, so you'd have your whole graph, and it would focus on a particular subset of nodes and edges called then the subgraph, and it starts taking away edges until you get a complete graph. But it might be that it just comes down to a single node and actually you never get a complete graph. And this is where this can become a very computationally expensive way of searching for communities of nodes, because it would have to go through every single node and every single size of grouping of nodes and create subgraphs for every possible combination within the whole graph. So it can take a long time for click finding to be done on a large graph. So it tends to be applied only in small to medium sized graphs. And it's one where clustering and community detection, which are often used with larger graphs, might not be appropriate. So it can be implemented using list find cliques, and it will list out any cliques that are found within the graph with the nodes contained within that clique. Or you can do a simple number of cliques and find if they happen. It's a slightly faster algorithm just to find the number of cliques rather than listing them all. Right, clustering coefficients. So for each node in a graph, the number of complete triangle subgraphs is calculated as a fraction of the possible complete triangle subgraphs. What this means is that you take a node and then look to find triangles of off of a particular node. So that means that you're looking for where a node is connected to two other nodes, and those two nodes are also connected to create a triangle. And then it'll go around and say, okay, how many of those are possible and how many of those actually exist? And this is a way of being able to find out how much particular nodes are clustered together, whether there are these complete triangles nearby, and whether they are existing, or whether they could be, but they're not there in the graph. And so this is a less computationally expensive way of finding groups of nodes and how they group together, and is often used with large graphs. And as a rule of thumb, kind of go large graph is a graph which is has 200 or more nodes. And I find this a really useful approach. As I said, clustering together, you often see those services that are working very closely together, and it tends to be by geography, and then that breaks down into kind of the different subgroups of services that are working together. Yeah, and it's a great way that you can color nodes based off of the clustering coefficient to be able to represent this visually. And again, we can run this simply using the clustering function, and it returns the clustering coefficient for all of the nodes. So each node has a particular clustering coefficient value. Eigenvector centrality. So I've talked a little bit about this already, so I won't dwell on it, but yeah, this goes beyond connectivity and the way that degree describes it in the nearest neighbor terms. But this goes beyond that and sees how nodes are facilitating connections across the network. And eigenvector centrality is pretty much in terms of understanding connectivity, it's the metric which is most commonly used. And it's really useful in terms of health services and looking at health systems, or social networks, because you're seeing the person or service which really is the facilitator of care. And in mental health, we tend to see it's quite often services like liaison psychiatry, the crisis resolution and home treatment teams, who are these core kind of caregivers. They react, they're seeing people in crisis, and then they're referring on and moving people between different services within the system. So it's a really interesting way to be able to look at the structure of a healthcare system. And I'd love to be able to look at this with some primary care data and some acute care data, because to be able to see which teams, which departments are really facilitating that care and being those core movers and shakers. And I think it's also one that, in terms of the teams that need support to be able to do that facilitation, it's a great way to be able to communicate that to management and others when making a case for improvements within services, that it's these teams who are doing the facilitation who need to be supported to be able to do that. So eigenvector centrality is an approximation approach, and so you can get more accurate measures of eigenvector centrality by changing the number of iterations that it runs. But obviously, the more iterations, the more computationally expensive it becomes. But yeah, a really useful one for coloring or doing the sizes of nodes, and we will look at that this afternoon. Isolates. So we can easily identify the isolates in our graph. So these are nodes which are not connected to any other node by an edge within a graph. And it's just a quick and easy way to be able to say, okay, who isn't actually interacting or referring to other services within the system, who kind of sits out on their own. And you can get which nodes are the actual isolates and the number of isolates returned using simple functions in NetworkX. Right, link analysis. So PageRank, this was developed from social network analysis, and it was a way that was used to rank web pages based on the incoming links to a vertex. So this is about where, how many different sources and how useful a source is referring to a particular web page. So it's like having somebody placing a link in their web page, linking to another web page, or whether the links come from Google or from Bing, DuckDuckGo, whether it's embedded in somebody else's website. How many links are coming from a particular source, and how good is that link? So it's more about the quality of incoming links determines the page rank of the vertex. So this is an alternative to other centrality measures, such as eigenvector centrality. So the neat one here is that PageRank is equivalent to the probability of an edge being traversed within the network. And we can actually build up a probabilistic network model using PageRank. So It's about the weight, the amount of activity along an edge. It's best used with weighted directed graphs because of this. That's when it is most useful. And so you could actually say, what is the probability that someone in service A is going to be referred to service B, or service C, or service D? And in this way, we can actually start looking at predictive models of service use as well. And I've got some interesting plans myself around that. So PageRank, again, is implemented very simply in NetworkX, and gives PageRanks for each of the individual graph nodes within the graph. Right, shortest paths. Pathfinding is a common task in network analysis, and it's seeing how distant two nodes are from each other. So it's perhaps, in terms of healthcare, one way to think about this is understanding how services are separated by other services, and for identifying common care pathways. I think there's some interesting applications here around the design of care pathways. Quite often in mental health, there aren't defined care pathways. That's something that's changing now, and there's been a lot of work to kind of come up with some predefined care pathways for particular cohorts of patients. And this could be a way to actually identify possible care pathways and to improve their efficiency. Looking at, unnecessary referrals that into services that might not actually be necessary, that people could move more efficiently between the service that they're in and the service that they need to go to, without going through intermediary services. So we can look at the shortest path between two nodes. We just name the source and the target node. And there are a few different methods along which it will try to find the shortest path. And this is all to do about minimizing computational resource, because it will often be using things like a random walk. So it will just be randomly trying different paths between two nodes to try and find the shortest, which in a big graph can take a while. And we can even just see in the first instance if there is a path between two nodes before going on to calculate it. Right, similarity measures. So this, I mentioned, is a really interesting set of approaches for looking at what the actual difference is in the structure of a graph over time. And this is where we can directly compare two graphs, and looking at the number of edge and node changes that might have happened between two particular snapshots of a system. And so this is done normally by looking at the number of changes that need to be made from one graph to another to make them isomorphic, to fit directly on top of each other and become the same. So while this is a really interesting approach, when we're looking at larger graphs, that particularly looking at whole systems, whole healthcare systems, this becomes an NP hard problem. And yeah, you probably heard Dan and Mike and Tom talk about these, that these are problems that they just take extraordinarily long time to solve, because there's so many different possible changes that you could make. So we use approximation approaches to this to try and find the minimum cost of editing the paths and trying to find the minimum number of edits to the graph to make them the same. So we can compute just a distance value, which is showing just a single value that says how far graph 1 is from graph 2. Look at the optimal edit paths. So that is where the minimum cost for transforming G1 to G2, or graph 1 to graph 2. And then actually returning all of the edits that would be required to transform one graph into another. Okay, I'm going to call a little break there. That's probably had more than enough of me talking about graph metrics for the time being. I suggest that we take 15 minutes and then we'll come back and do a little task of doing some network analysis on some Game of Thrones data. So if we come back at 10 to, if we come back at 10 to 11, that will be fantastic. I'll see you all shortly. Okay, welcome back, everybody. Hope you're all suitably refreshed and got some nice beverages ready for a bit of task time. So, without further ado, right. So now let's have a go at actually analyzing some graphs with Network X. So for this task, you're going to use, there's a file all prepared for you, mainly in the main, with its analysis task.py. And so this file contains the data import functions, data import functions, a graph builder function, and the base of some basic analysis code as well. Along with this task, there are two data sets supplied. There's node and edge data describing the character associations for Game of Thrones seasons 1 and 2. So these can be found. So in the Git repository that you've downloaded, in 4C in graph metrics, you'll find the task folder. You've got the analysis task py file, and in data you'll find the season 1 edges and nodes and season 2 edges and nodes files as well. There is CSVs. So your task is this is the one. I'm going to try and remember how to zoom in now. That's there we are. So the code in the file, we've got the imports for network X and pandas, got the create graph function, and we've got the data import functions here. Then run to create the graph, G, and there's a series of analyses as well that can be run. So the aim here is to go through to adapt the code so that you read in season 2 data as well, and then to conduct an analysis of both of season 1 and season 2, and to compare the 2 seasons in terms of the character association networks that you get between the 2. And so, yeah, compare the various metrics for both seasons, adapt the code for seasons 1 and 2, compare the various metrics for both seasons, and then come back and tell us something interesting you found about the analysis is the idea. So I'm going to put you into your breakout rooms. You'll have the slide set, so use that as a bit of a guide for you, and a bit of a reference. There's also the link to the Network X documentation, so you can have a look at. There might be other metrics that you want to explore. You might want to look at adapting them using some of the arguments rather than just the defaults in the various functions. But yeah, have a look, and we will come back at 11:30 to have a look at those. And you can either get hold of me on Slack, just drop a message in the either directly to me or in the module channel, and I will come and help you out, or I'll just kind of be floating around and popping in and out of the rooms as well. So I will pop you. Okay, so now on to advanced network analysis session 2, graph visualization. So we're going to go through, as mentioned just now, how graph visualization works, some of the layout options that you have with standardized algorithms and predefined coordinate systems. Then look at Network X, Cytoscape, and Gephi as different options for your visualizations. So we're going to aim to understand how graph algorithms seek to represent data, know how to visualize graphs using a variety of open source approaches, and be able to customize a graph visualization to improve its usefulness. So, how graph visualization works. Network graphs are essentially multi-dimensional objects that, in Python space, that enable us to visualize, to contain and to visualize and use multiple attributes of the data, and we can have lots of different layers to our data. But the three main components of the graph itself that can be customized to represent different aspects of the data are the nodes, the edges, and the layout of the graph. So when we're looking at node customization, we're able to change this kind of array of different things about the nodes. And the important one is to think about what the type of data that we're embedding within the node itself. So some of these work for continuous attributes. So continuous data, so with the size, for example, if we're looking at embedding things like eigenvector centrality in the size of the node, then that's a continuous attribute, and size works really well for that. We can also do color, and color works very easily with discrete attributes. So categorical data in particular, so trying to show the difference between so you've got a social network with looking at people's look at what, and you could embed that attribute as the color of the node themselves. But we can actually use color as a continuous for continuous attributes as well. And we'll see an example of that in the cytoscape visualizations, where we do color interpolation. Then we can also do shape. Again, this works best for this works with discrete attributes, so we can change the shape of the node to show something like whether somebody takes jam on their cream on their scone or cream on their jam. Then we can also do opacity, so that's how see-through, how the transparency of the node itself. And again, that can be used for continuous attributes because opacity is a continuous gradated scale. We can use labeling as well for discrete or continuous attributes. With edges, we can change things such as the thickness of the edge. And this is normally used for the weight of an edge to be able to show how much activity there is along a particular edge. We can also use color again on the edges, and commonly this is linked to the edge from which the source node of the edge. So it will be the same color, the edge will be the same color as the source node in a directed graph. Or we can use edges to represent something else, should you wish to. And again, we can use labels, labeling for continuous and discrete attributes on the edges. So layouts with network graphs is an interesting, complex, weird subject, because in some instances with small, simple graphs or with highly organized networks, it is very easy to come up with a simple layout for your network. And these kinds of simple layouts work when you've got these very organized, either hierarchical or highly organized systems. So things like the bus layout, where you have a central line, and it's actually your nodes are coming off of a single stretch of off of a single edge, or things like a ring when you have a circular network, star when things are linked in to a central point, trees when you have hierarchical, almost like a family tree layout to structure to your system, a mesh wherever you have everything highly interconnected, or you can have hybrids of that. And these kinds of network topologies actually really only work with highly structured systems, and are particularly used with planning for things like power distribution networks, computer networks, that type of thing. So healthcare systems are often not so highly structured, and are often more complex and quite a hybrid of multiple different network topologies. And this makes them much more difficult to visualize. But there are algorithms that are there to help with visualizing these complex networks, and that have more haphazard random layouts to them. So in Network X, there are a few different core layouts which can be useful. Sometimes, if in doubt, it's quite useful to use a circular layout to just get your nodes positioned in a circle, so that you can start to get an idea of what is going on. It's kind of the simplest layout that you could go for, just to organize a larger network. Then we get things, the Kamada Kawai layout, and this uses a path length cost function. You're welcome to read the documentation on that. Basically, it works with keeping, it's kind of towards this clustering idea that nodes that are highly linked together are closer together, and those that are more distantly linked or less connected with other nodes in the network are more distant. And that can work okay if you get the parameters for the layout correct. Random layout, which just positions the nodes uniformly at random, so they just kind of end up in a decently laid out block, really. Then we get the spring layout, or Fruchterman-Reingold force-directed layout. And this is a physics-based algorithm which works using attraction and repulsion between nodes that are either close together, and that when you get groups of nodes, they'll attract nodes that are nearby, and those that are further away get pushed out. And yeah, so they use normally, yeah, it's repulsion, attraction, and kind of using gravity-based parameters. Another is spectral layout, when nodes are positioned using the eigenvectors of the Laplacian matrix. Basically, this just tries to spread the nodes out in clusters, essentially, So keeping those that are closely linked together, and pushing others outwards. And then we get spiral layout, which is where the nodes are just positioned in a spiral. There's a link here for the NetworkX documentation on drawing graphs, and that has all of the information around the different arguments that can be used with these different layouts. So the other one that we're going to look at as a Python-based approach is Cytoscape. And this, again, has a few standardized layouts. You can use a preset or predetermined coordinate system. So you, actually, there was an interesting comment from Matt Eves, who was talking about representing actually position in the network relative to physical position, so using a geographic coordinate system. And yeah, this is something that is is not commonly, but can be done and is done and is used particularly with urban planning and looking at transport and logistics, which commonly use network-based approaches. And so you can base the layout of your network on the geographic coordinates of the locations of, say, your services or where people live. Cytoscape has a random layout in there as well. It has built-in grid layout, and it's either a square or rectangular grid. There is the circular layout in there as well, which is self-explanatory. Then you've got a concentric layout where you get nodes positioned in concentric circles. And then you get breadth first, which is more for this hierarchical tree-based structure. So that works when you have a much more hierarchically organized system. The most useful of the Cytoscape layouts that I found for visualizing healthcare systems has been COES, which is similar to the Spring layouts in NetworkX, and is again a physics-based Spring simulation, force-based layout. So there's more detailed information. I've given the links here for Cytoscape for the reference material and specifically for the layout reference as well. There is, along with Cytoscape, there's also extra additional layouts as well. And you get a variation on the COES layout, which has been extended for nested structures. So if you have graphs within graphs. There's the COLA layout, which is again another physics-based layout with which is kind of good generic applicability. You get the Euler layout. It's another physics directed layout and is pretty generic. Spread is all about achieving an even spread of the nodes. And then a couple of more specific ones, DAGRI for use with directed acyclic graphs and trees. So this is where you've got a much more highly structured system. And Calais, which is a discrete layout algorithm. Not actually one that I played with, so I can't recommend on that. But again, these, if implementing these additional layouts, when we do our imports below that, we've got to add this additional line of loading the extra layouts, cyto.load extra layouts. And that'll enable the use of these additional layouts. So that's kind of just giving a bit of an overview of the kind of ways that the Python packages, the types of algorithms that they're using for creating network layouts, and kind of how they're based, whether it's using geometric shapes or they're using force-directed physics layouts is the more common ones. So when we're doing graph visualization with NetworkX, if you remember from the introductory session, we create our graph object first of all, and then we pass the graph object to a layout function, which is, and the layout is the name of the layout we want to use. So that could be spring layout, or the it might be random or circle. And we pass the graph object in, and that returns a set of positional coordinates as an object. And then to draw the network, we then pass the graph object and the position dictionary, the position object, into the draw network X function. You can also pass the layout directly into the draw network X function. There's just an alternative way of doing that without creating the dictionary separately. So there's a number of keyword arguments that allow us to be able to customize what a NetworkX graph looks like. And this is where we can start embedding information within the graph around things like the node metrics or additional attributes that we might want to put in there and display in relation to both the nodes and the edges. So these are the keyword arguments that we're able to pass in. So things like when we're using a directed graph, then we can change, we can say we want arrows, we want the arrow, change the arrow style and the arrow size. For the nodes, we can change whether there are labels on it or on them or not. We can modify the node size, the node color, the node shape, or use a color map to produce gradated colors, which is where you're using more of a likely a continuous attribute for color, that you'd use a color map, that color gradation. And these take, for example, with labels, we'll take a Boolean argument saying true or false. Node size itself, you can pass in a dictionary or a list, which then allows you to define the node size for each individual node. And same with node color, that you need an object that defines the color for each individual node. Or if you pass just a single argument into it, it will set the size, the color, or the shape to just, they'll all be the same. So you could set all the nodes to red. So with the edges, we can set the width, and this is important if we want to visualize the weight of an edge, so the amount of activity going along it, and visualize that with by changing the width of the edge relative to the weight. We can use edge color, as I mentioned. That's often used as it's the same color as the source node from which it's leaving. You can pass a color map as well if you want to use continuous color attributes, and you can change the style slightly, so you could use different line types for the edges as well. You can then customize the fonts in there as well for the labels on your nodes and edges. So let's have a little look at an example. So if you'd like to open the network_x_viz example .py file, this you will find in 4D graph visualization folder. In the examples, there is then network_x_viz example. And you can open that. Open that in Spider. I'm just going to do that myself. So you might just want to, if you're just using a single screen, just have Spider open. I'm just going to talk through the code here a little bit and just break it down for you. So at the top of the code here, I'll have it open, but you might just want to have your own Spider window open, but I've got Spider open here and just going to talk through the code. So we have our imports at the top, and then I've just, rather than importing some data, I've created some simple graph data here. So our nodes are a dictionary with list, which is the ID, and then a label for the node. And then you've got the source and target lists as well for the edges, and a weight for each edge as well. So pass those and convert them to a data frame, each of those. And then we can go on to then use the standard, what's now probably becoming familiar, this graph to this function to create the network_x graph object. And then we can then down the bottom, we see we're defining the node positions. So there's the opportunity to have a play with a few different layout options. Then I've also got an n size variable here, which is a list of sizes for the nodes. and then a list of colors as well. These are given as hex codes for the colors. I prefer to use hex codes, but you can use RGB color codes as well. And then we get the edge, creating an edge size object, which is here, interestingly using a function called getEdgeAttributes. And this allows us to pull out the weight attribute from the edge data. And we can use that to define the edge thickness. And then there's also edge color, which is given here as an array. Set up a shape definition here, and alpha, which is the opacity of the for the nodes themselves. I'm just going to flick over to the documentation as well to show you in there, because there's a lot of, no, not that. No. So here in the NetworkX documentation, it gives the different, if we go, here we are, here's the different graph layouts that you can have. These are the layout functions that we call to be able to get those. And let's draw NetworkX. And here it gives you all the different additional arguments as well. And so the drawing in matplot in NetworkX is based on that matplotlib. So things like the node shape, for example, is defined by the matplotlib marker codes. So you could find them by going to matplotlib, marker points, that's what they're called. So here we see the full list of different marker points that we could use with NetworkX. And for example, I've called D, which is the diamond shape, but you could use any of these different marker shapes by using the code here. And then, yeah, we use this, the nxDraw function and we can pass in our different arguments to that. And in addition, so it doesn't, it won't automatically draw the edge labels on a NetworkX graph. You have to pass that in as a separate argument afterwards, draw NetworkX edge labels some little quirks of NetworkX there. So if I just run this quickly and show the output. So the plot here is displayed in the plot window, and here we've got our arrows shown on our edges. We've got our diamond shaped nodes. They are all colored as we specified, and we've got edge labels as well with the different weights. So NetworkX is a relatively simple, produces relatively simple network visualizations. It is in many ways much better for the analysis side rather than the visualization. But if you are just wanting a nice simple network, simple graph visualization, or you just have quite a small graph, then NetworkX is a nice, easy little way to do that. What I'm going to recommend is that kind of using the NetworkX viz example as a basis, that you might like to go through and have a play with changing the attributes. Perhaps even look at using some of the graph metrics if you're feeling a bit daring. Perform a small analysis and then use that analysis output as the input for the graph visualization. See if you can work something out there. We'll look more at doing that with Cytoscape after lunch. And yeah, just have a go at changing some of the attributes here, what they do, what formats they need to be going, look at what formats they need to be being passed into the drawing argument, the drawing function. And even you might want to import or import some additional data. So using the Game of Thrones data, for example, and try some different layouts with that. Or some different layouts with this existing data, or feel free to extend it. But it's kind of try to get an idea of what you can pass into a NetworkX visualization, and what you can display within it. So I'll stop sharing now, and oh, sorry, I should have made that a bit bigger for you. Apologies. But you've got these, you've got this file. So if you want to go through, I'll put you into your teams, and then if you break for lunch at 12:30 until 1:30, and then we'll come back at 1:30 and we'll look at Plotly Cytoscape and hopefully create some a web app with a great network-based visualization. So I will open the rooms, and I will see you all at 1:30. So this afternoon, we're going to continue on with visualizing networks, and what we're going to get into next, after having a look at Network X this morning, we're going to go on to look at Cytoscape, which works in Plotly Dash. So you might not have heard of, you probably heard of Plotly, but you might not have heard of, of Dash. This is a Python framework which is designed for building web applications. And within Dash, you can use a powerful network graph library called Cytoscape. And this allows you to create interactive graphs within web applications. And so if you remember back to the introductory session a couple of weeks ago, two of the examples that I gave were of a Game of Thrones network analysis app and a systematic review app as well. And both of these were built in Dash, and we're using Cytoscape to render the network graphs. So what we're going to do this afternoon is we're going to go through and we're going to look at how you create a simple Dash application that contains a network graph. So a bit of a double whammy here, a bit of web application development and also network graph visualization. And then if we have time, we'll go on to look at Gephi as well. So Dash applications. Dash applications have 6 core sections to them, and they go in this very specific order. So the first part is that we get all of our Python library imports first of all. Then we go on to what's called persistent local variable creation. So these are any functions or variables that are created when the app itself first starts, and they are only run once. Then we go on and we initialize the application. Sorry, I've got a window up, which isn't very helpful. Sorry, then we go on to initialize the application. Then we give the application layout. So this is the actual structure of what is the visual application itself. Then we write a series of application callback functions, which enables us to interact with objects within the application. And then finally, there's the application run command at the very end. So we're going to step through these bit by bit and just look at each section. So as is common with any Python script, we normally, the first thing we do is import the required libraries at the beginning of our script. And with Dash and Cytoscape, the most commonly needed libraries are the core Dash import itself, Dash package. Then there's the Dash HTML components, which are used to build up the HTML-based layout of a Dash app. Then there are Dash core components. We'll go through these in a bit more detail in a minute. But this is a core library that you'll bring in every time. Then when using Cytoscape, we import Dash Cytoscape separately. And then in this instance, we're going to bring in Network X as well. That's a useful one because that allows us to undertake an analysis of our graph and then pass that out to the web application. And when we're using callbacks to enable functionality, you need to use from dash dependencies, we import input, output, and state. And again, all this will become more clear as we go through the rest of these sections now. So persistent local variable creation. After we've put in our inputs, we want to run anything that's going to run just once when the app is originally set up. And it's these, particularly for simple applications, where you don't need lots of interactivity and you have local variables never change, these can be really useful, as it saves having to do reactive programming with bringing in the callbacks. And in the example that we're going to look at, all of the data is brought in and the pre-processing of that data is done when the app first loads. And we can also set up style options for the network graph in something known as a style sheet. And this term comes from web development, which is CSS style sheets. And CSS is the coding framework that's used to style web pages, and sits behind any web-based application, providing it saying, we want this font here, make this big, make this color. That's what happens in the CSS style sheets. So we can declare those as well. So when we initialize, once we got our local variables, we can then go on to initialize the app itself. And it only requires 2 lines of code to be able to do this. We first of all create a dash application object, and kind of the variable name can be anything, but kind of the common name to use is just app. And we assign a dash object to that. So call in the dash package and it creates a dash object. The second line then creates a server object linked to the application object. So these 2 lines, when using dash, don't change. They always stay the same. So then we can go on to declare our application layout. And the layout contains information on how you declare all the objects to be used in the application and how they're structured and set up on app initialization. So the information passed in here, this information is all passed into the layout component of the application object. So just at the top of this image here, and again, I'll go through this in the example script, but up here we have, we're declaring our layout to app.layout. And that's just so that the layout goes straight into the app object and is located properly within there. And the layout itself is based on HTML components. And so if anybody's got any web development experience, this will be familiar to you. But the syntax itself has been adapted for use in Python and within the Dash API. So if we look at the image here, we can see that we're calling from the Dash HTML components here. We're calling a div, which is a divider object. That these are used in web development as containers to be able to wrap up different objects and contain them within a single unit that CSS styling can be passed to. And it helps to structure the app layout, the web layout itself, because we can add things like spacing, columns, and different rows by using div objects. Then you'll also see here that we've got things like H1. This is a header of size 1, which is the largest header type. You get H1, H2, H3, H4, H5, and H6, which means that you can have these different header sizes as standardized sizes. And these are found within HTML programming. Just another one that's up here at the moment is a HTML.p, and this is a paragraph. So that stands for paragraph. So there's a little bit of learning about web development when creating these applications, but they're also, when creating simple applications, this kind of level of programming is really quite straightforward. So in the application layout, we can build up the structure using HTML components, Dash core components, and additional libraries such as Site Escape and Dash Bootstrap components as well, which are some additional community built components as well. But yeah, we get, for HTML components, some examples of these are the divider container, the headers, H1, 2, etc. Paragraph objects, so we can have a paragraph of text. Hyperlinks, which are given using A. We can do lists, so unordered lists, which is UL, or an ordered list is OL. And things like images. So images we can bring in using the image object. So these are kind of the main kind of non-interactive parts of your application. They're things that aren't actually that the user can't really interact with, and that are just static within the web application. The Dash core components, however, these are those that are interactive. And so these are things like drop-down menus, input boxes, slider objects, buttons, graphs, and checklists. So once we've got all of our layout set up and our objects in that we want, we then got to make it all kind of work and do something. So this is what callback functions are for. And these are, they take inputs from the app components that are defined in the layouts and return outputs to other objects in the layout. And the syntax is an adaptive version of the standard user-defined functions in Python. So if we look at this one here, the main difference is that to start a callback function, we declare @app, so the name of our app, dot callback. And so this means that we're passing that this links the callback function directly to the layouts. And we can pass in outputs, inputs, and also states as well. So when we get the first thing we define is our outputs or outputs. We can also declare multiple outputs in a single callback function. And this just means that you need to give your outputs as a list, so in square brackets, like here with the inputs. But here we're just passing one, returning one output, and this is going to a network graph called dynamic net. So we declare the name first, and then we say what it's going to, which part of that object. And as we'll see in a bit, Cytoscape network graphs, their data is passed into the elements component of the object. And here we have two inputs into this function. One being it's actually a hidden storage element where some data is stored, and so we're retrieving that from this hidden storage container, and also getting an input from a graph from a slider object and getting the value from that. So the function itself is then set up in the same way as a normal Python user-defined function, that we give a name for the function and the arguments that are going in. Now, the arguments are the inputs here that are declared in the callback. And in this instance, we've got some data going in and a value. And so here I've just declared that the data is coming in is called data, and the value of the graph of the slider object is called selection. And then you give your function and what's actually going to happen. And then you have your returns, and the number of return objects should be equal to the number of outputs. So we'll go through and list out a whole load of functionality that we want in our web app. And then finally, the final thing that needs to be done is to declare an application run command. And the application run command does just that. When it's at the bottom of the script, it runs the application itself. And again, these two lines stay exactly the same. So let's have a little bit of a closer look at an example of the Cytoscape graph object, as this is the main thing that we're going to be working with today. And so here in this very simple app layout, we just declared, so we got the name of our app, .layout. And then first of all, as is just common in web development, that we wrap these in every objects are wrapped in containers, which are the div objects. And there's an interesting little quirk in Dash that if in HTML objects, anything that is passed to it sits within what's called the children argument. And this is to do with the hierarchy of web development, so that you have a parent and then you will have the children below it, and the parent, the children are always contained within the parent object. And so this just kind of makes this explicit in Dash, that we declare children argument and then pass it a list of objects that sit within that particular element. So the site escape object itself is sat within the children argument of the divider object. And here we have calling the site escape package, and a site escape graph is site escape. And then we open and we can provide it with a whole load of different arguments to set up, get the graph set up. Now, in some ways, the most important in Dash is this ID. And so all objects are given a unique ID. And this means that they can be identified in the web application and in our callback function. These names here are the IDs that are given to our objects here. So we need to make sure that there is a unique name, a unique identifier that is given to any object that we want to interact with. Then we can pass in a class name if we want. And when I say class name, this is a CSS class, which provides some formatting to the object itself. Not a necessary thing, but when you get into making your apps look nice, it's very useful to be able to create these CSS classes and provide standardized styling without having to explicitly declare it for every object. Then the next most important thing is the elements argument. And as I mentioned in that previous callback, the elements part is, this is where the data for the graph is going to go. And this is what all of our pre-processing in the app that I'll show you is going to be working towards creating. And we'll look at the structure of that in a bit more detail. Next, there's some style arguments, which are passed in as a dictionary. And there's different keys that can be used to define certain style attributes for the object. In this instance, this is the width of the object, the graph object itself, and the height as well. And so this is declared as 80% of the total screen width and to a height of 600 pixels. There's a lot of interesting different kind of ways of defining things in HTML and CSS. And that's a whole 2 weeks going through that, or at least another day's training session. But as an overview, we can pass style arguments in and customize different parts of the object explicitly within the object itself. Alternatively, these style bits could be passed in as through the class, through the CSS class. So then we go on to declare the layout for the Cytoscape graph. And here, this name you might recognize from this morning, that we've got using the COS layout for the network. And then there's a series of different parameters that we can set as well. Now, this list is not exhaustive. There's more parameters that can be set for this layout. And there are links to the documentation earlier in the presentation for that. So here, declaring the name of the layout, and then things like the padding, node repulsion, gravity range, nesting factor, edge elasticity, ideal edge length. These are all things that, because this is a physics-based layout, it's working out in the algorithm how to push and pull nodes away from each other. And again, this layout is declared in a dictionary format. The final argument here is a style sheet. And again, this is an additional CSS style sheet that can be passed in using the style sheet argument. And it's just called, in this instance, default style sheet. So just to, this just gives a bit of an overview of what I was saying there, that the ID is a string and it's a unique identifier within the app layout. Class name is again a string, and it's a CSS class with standardized styling options. The elements is a list of dictionaries for the node and edge data. And again, we'll look at that in more detail, as that's an important component of what we're creating. Then we get the style, which is a dictionary, and style options that can be alternatively placed either in the style sheet or in the CSS class. The layout then is defined in a dictionary, and the graph layout name is given and the attributes for that particular layout. And the style sheet itself is also a dictionary with node and edge styling options. And so the style sheet here is, this is an example of the one that we'll be using today. And what we do is we define the node and the edge styling here. So you get a selector level within the dictionary. So this is a, we're selecting node, and then there's the next key is style, and that itself is a dictionary of different attributes. So here, defining the height, the width and the height of a node, background color of the node, so the actual color of the node, any content for the node. This is a label that we can pass into it to label our nodes. Set things like the font size here, text outline color, text opacity, and text outline width. And there's, again, this is not exhaustive. There's a whole load of different attributes that we can set for the node's styling itself. Then, as another dictionary within this list, we can select edge, set to define the style parameters for the edges. And within the style, there is another dictionary, and here just setting the line color. But there are again a whole list of different attributes that can be set for the edges. So the easiest way to understand this is to have a look at what's happening in an actual Dash app. So what I'm going to do is I will just talk through the code quickly, and then I will let you have a look at and give you a bit of time just to have a play with it yourself so that you can see what's going on. So this is the simple app. It's not very, the code isn't very long, but this is a simple Dash app that renders a network graph. And so here we have our imports to start off with, bringing in Dash HTML components, pandas, and Dash site escape. So we're not using anything beyond those 4 libraries. The first 2 lines here, so what we're doing now is we are setting our persistent local variables in this first part here. So our persistent local variables in this case are, we're bringing in our node and edge data. So it's using the Game of Thrones season 1 data. And there's a function here to create the graph. And then following that, there is, we declared this style sheet for the node and edge styling for the graph itself. Now, what I'm going to do, I'm going to run this first bit here without running the app itself. Oh, got to set my working directory. It's always a good idea. It would be easier if I go to okay. So this function, and I recommend just having a little look at this more closely by yourselves and just pick it apart a little bit. But site escape graphs take their inputs as a list of dictionaries. And I'll show you what I mean by this. So the elements object that's been created here is a list of dictionaries. And each dictionary contains at its first level a data declaration. So a data key, that's the first key. And that needs to stay consistent for every single dictionary. Then you pass in an ID. So we have a unique identifier for the nodes here. This is a node, example of a node. So we give it an ID. And here I'm also adding to it another attribute, which is label. If I go down a bit further, we've got all of the nodes, but then we get into the edges. And again, so this list contains both the node data and the edge data. And when we come in, we still got, again, the first key, the first level, because it's a list of dictionaries that contain dictionaries. So it's 3 levels there. And this next dictionary, then we have 3 things, which are source, target, and then any attributes we want to pass. And here we're using weight. So the source and the target use the IDs from the node that are attributed to the nodes. And this is the same principle as we see in both in NetworkX and Gephi as well. It's always that principle of the nodes have an ID, and we use that ID to declare the edges, the source and target nodes. So that's kind of that's the overview of that there. So once we've declared, so basically we've read in our data, created these the elements list of dictionaries that contain dictionaries, and declared our style sheet for the graph. We then move on to the next core section, which is the initialization of the app. So we the app object gets initialized, and then a server object is initialized as well. Oh, I can see a question there.
Yeah, hi Sean. I was just trying to follow along and running the bit of code you did, and I can see it's done something. If I just type in elements and return it, it shows me the stuff in there, but they're not showing up in the variable explorer. Might there be a reason for that?
Have you just run the top piece of code here?
That far, yeah.
Yeah, without running anything else?
Yeah.
And making sure to run the create cytograph function as well.
Yep.
Yeah. The one to do would be to remove all variables and run it again. It probably just hasn't been passed to the variable explorer for some reason.
Okay, thanks.
So after the app initialization, we then declare our layout. And here we give the app name .layout. And this is, as you saw in that screenshot, that we have the divider object and then the site escape object within that and the arguments given to it. The final section here then is the run function, which basically just goes, if the app has been initialized, run the server and run my app, please. So where I just went, and I can run sections out of this just as I need. When we actually want to run the whole app itself, we need to make sure to run the script as a whole. And so making sure that we use the run file button, not just running the selection. So if I run that, what you'll see down in the bottom right in your console will then be, it comes up with run file saying, and then it will say running on http:// and then it gives an IP address. And this IP address is a development server that's running locally for you. And it actually throws a warning saying that this is a development server. Don't use this for production and deployment. That is solved in other ways. But just for testing and for your own use, just running it locally like this is the way to do it. So if I now go to my browser and type in the address, which is 127, I've used this a lot, so it's already up there, but you'll need to type this in the first time or copy it out of the console. And we'll see that the graph is rendered here on the screen in the browser. So just a couple of notes on running these apps. So you can see that this is still running and my console is active. So I can't run anything else in this instance of Spider at the moment. To stop it running, you can either press the red stop button, stop the current command up here, or press Control-C. Now this is important if you're copying out this address here, because you can't use Control-C to copy it. You need to right-click and copy that way. Otherwise, you'll stop the app from running. If I stop the app running here and then return to the browser here, it's gone, oh, it stopped, and it starts throwing errors here. But yeah, so normal shutdown is you just close the browser window with the app in it and then stop the app running here. So I think it would be a good one if everybody, I'll open the breakout rooms and just for 15 minutes, go through, have a look at this simple app, and then we'll come back and we'll look at a more advanced version that involves including conducting an analysis, including that in the visualization, and also using a callback to add some interactivity as well. So I think if we come back at 25 to, so just over 15 minutes, come back at 25 to 3, and we'll then go on to look at the next slightly more complicated example. Just contact me on Slack if you do need anything. I need to stop sharing. We are. Okay, excellent. So hopefully everybody managed to have a running, or within each group at least, there was running apps, and you're able to have a look at the code and just the structure and how, and just interrogating it a little bit about, you know, what we're doing here in terms of extending this use of Python for not just creating a static graph, but actually being able to create something which is web-based, shareable, and interactive. And now we'll look at how to make this type of graph truly interactive and a bit more useful. So what I'm going to do now is show you the advanced visualization here. So this is the Cytoscape Viz advanced.py file. And so, okay, so I'm going to talk through this again, as there's quite a few more functions up front, and there is also now a callback in here as well to add some additional functionality. So I'll talk through how this has been built up. So first of all, we've got a few more imports coming in that we need. So here we've got dash core components being brought in, NumPy, being used, matplotlib being brought in here, and also from scikit-learn, there's this thing called standard scaler, which we can actually use to rescale numbers onto a common into a common scale, and basically normalize the data. And we're also bringing in the dash dependencies, input and output. So again, using the Game of Thrones season 1 data, bringing that in. And here, as is becoming very familiar now, is the creation of a network X graph. So this function is being used to create the network X graph, so that we can conduct an analysis on that graph, because network X is the more powerful library for doing that. And then we can basically use that analysis and visualize it within the network graph. So there's a function down here called create analysis, and it gets a little bit long-winded, but if I just talk through it briefly, hopefully it will all make sense. So what gets passed into this is the graph object, the network X graph object, and the node list as well, because what we're wanting to do is attach the analysis, and so the analysis that's done on the graph to the nodes themselves, so that that analysis can be used when we create the cytoscape graph elements. So the analyses that we're doing here is eigenvector centrality. So we get the eigenvector centrality of each node, the page rank for each node, the degree, and the betweenness centrality. So these are all different measures of connectivity. And so by using these, we can look and see just how they differ slightly. So then we got to extract the analysis and convert it into a suitable scale and format. So what's happening in this section here is just converting the analysis outputs, network X analysis outputs, into data frames so that we can easily work with them. Then here we have a list of these different data frames, and then we squish them together, concatenate them. Then take these and take that and rescale or normalize all of the analysis values so that they fit together, and are on the same scale. And then there's just a little bit of normalizing, because it normalizes around 0. It's just bringing everything up so it's from 0 upwards. It's all positive numbers. Then we just bring all of this together, these original values, with our oh yeah, that's so we're going to bring our original analysis values together with the now standardized ones, and then based on those analysis values, we're going to color the nodes themselves, and select a color. Now, this took me a little bit of fishing around. I've been meaning to do this for a while, but it's basically, it's called doing something called color interpolation, which is Matplotlib does this for you on its own very nicely, which is very, very kind of it. But it kind of hides and only works with Matplotlib plotting functions. So those the color maps that Matplotlib produce, those nice gradiated color maps, only work with Matplotlib or compatible type plotting. And unfortunately, it doesn't work with Cytoscape. So what I've actually done is I was able to find, I've got to give credit where credit's due. I've just adapted it slightly, but I found this color interpolation function called color fader here. And what it does is it creates a linear gradient between two colors. And the node color picker function here, so our create analysis function calls the node color picker function on each of these analyses, on each of these data frames. It then goes through and it, for each of those analyses, it works out what is the top and the bottom of it and picks the colors in between for each value in that analysis. So basically down here, we're passing in to color fader here each individual analysis value, and then appending that to a new list, translating it to a data frame and passing it back out. And yeah, this is, I highly recommend using this and ripping this off if you need to do color interpolation, as this is the best solution that I've come up with so far. And so this then returns a full color scale for us, which we can use to color based on the analysis values. So the output that we get, and I will just run this so that you can see. So what we get returned is the original values from the analysis here on the left. These are the eigenvector centrality, page rank, degree, and betweenness centrality values. We then get the colors that are attributed to each one based on the linear color scale, and then the standardized values which have been used to create these colors. And so that, if we then run elements, you'll see that we're creating the graph data in the same way, but this time the nodes not only contain an ID and a label, but also all this data on the betweenness, centrality, all these different connectivity measures, the values for that node, and the relative colors relative to its these values. So we've just extended the elements which need to go into the site escape object, and given it a bit more data that it can now use, that we can now use to do other things, and actually style our network graph. So you'll see here that in the style sheet, in comparison to the simple example where these are all preset values, the width and height of the nodes is now set relative to the centrality value. The background color is now the color that's attributed to each node as well. So we can declare these in the style sheet and they'll be picked up from the elements object. In the app layout, the site escape graph object remains exactly the same as before. We just got the slightly altered style sheet going into it. But here, I've also added a drop-down menu from the dash core components. And this drop-down is so that we can select and change between whether we want to view the nodes as the analysis for eigenvector centrality or for PageRank or degree or between this. And so just setting a few parameters for the dropdown, we give it a unique ID because we're going to use that in our callback function. So we need to make sure it's got an ID. Then there's a few little things that I've set here that are clearable, false, so that there is always a value in the drop-down menu. Multi is false, so you can't select multiple values. Set an initial value, which is sent value, so that's passing an initial string in. And just a little style option just to set the width of the drop-down to 200 pixels. So next up is where we actually use the input from the drop-down to determine the styling on the graph and whether we're going to be using which color and metric value we should be using. So here we got the input as the analysis metric drop down, and we're getting the value from that. And so in the options here for the drop down, we got a list of dictionaries, and these dictionaries can contain a label and value key pairs. So the label here is what you'll see in the drop down, and the value is what's returned by the drop down when that label is selected. So instead of, you could have the labels and the values be exactly the same, but you tend to have the label as something human readable and the value as something that is recognizable and more easily processed within your program. So here I've got eigenvector centrality, but the value being returned is sent value with an underscore as a complete string. And so we can take that value, and that's passed into this callback function. And it's saying that if the value is sent value, then I want to create a string variable that says data sent col, and the val variable is going to be a string called data sent val. And so these are what are going to go into the into a new style sheet And so we got them here for rank value, for degree value, and betweenness value. And then what we get here is a new style sheet. And so this takes the same structure as the default style sheet that created previously. It's a list of dictionaries. And here we're just defining, because we're just defining what we're changing in the style sheet. And this is for the selector for the nodes. The style that we're changing is the background color, the height, and the width. And what we return is a concatenated list of style sheets. Because these are the style sheets themselves are lists, we can use the plus operator to concatenate the original default style sheet with the new styles, and that'll overwrite, the new styles will overwrite the old styles. And that will then be passed back out to the cytograph object, and it will be put into the style sheet component of that object. So I will just show you now quickly. I'll run this and then I'll let you have a look for yourselves. So now we get a different colored graph with different size nodes. And then we can click on the drop down and change the size and change the analysis metric that's being displayed. One other thing that is available in here is that there's a section in the create analysis function where I can exaggerate the size of the nodes by changing them by set values rather than using a standardizer. So I can uncomment, there's instructions in the comments here on how to do this. But I can uncomment parts of this. And I just comment out this. Cool. And if I do that, and then reopen the app, should get significantly different sizes for the nodes. So just a little thing to have a play around with there as well. And I would encourage you to have a look at the Cytoscape documentation to have a play with some of the layout options. So just a reminder, the links for that documentation is in here. So we get the Cytoscape, oh, better copy that. And here in the layouts, we get all the different layouts that are available and all their different arguments as well. These, as long as they're entered in the dictionary format. Most of them should work. If you do get an error, it's because this documentation is actually written for JavaScript, the JavaScript version of Cytoscape, rather than specifically for the Python version. However, most of these arguments do work and are fine. So yeah, have a little look at that, have a play, and we'll just have half an hour. If you might want to even have a look at the Dash documentation. And you might feel that you want to have a go at adding a component or having a look at anything like that. You just need to go to Dash Plotly. You can either go use this link here to go to the Cytoscape reference, or down the bottom, did I put straight Dash in there? No, just use, oh yeah, Dash, there's the introduction there to Plotly Dash, a link to that. But it's quite easy to Google. And you can have a look at all the different options that there are for different components that can be added in to your apps, and just have a little play with that just for half an hour. Okay. So what we get, I apologize if these are a little bit small. When you start a new project in Gephi, what you get is this, met with this main screen. I've got zoom ins on all of this, so don't worry about the detail. And this is the overview page, and this is where you can start building up your network once you've got your data in. Because there are three main screens: the overview, which is what
Sean, I think that you're not sharing the screen.
Oh, sorry, you're not, are you? Thank you. So we get the overview screen here now that you can see it. And at the top, you've got the toolbar with overview, data laboratory, and preview. And so the overview is all about tweaking getting the layout, the appearance, and the analysis all worked up in there. The data laboratory is where you can either manually enter or upload your data for the visualization. And the preview gives you refined appearance parameters and the ability to export the images. So the data laboratory is where you need to start, and you can upload your node and edge data into here. So the easiest way that I found, and the way that we'll do it today, is to import spreadsheet, use it, and import a separate nodes spreadsheet and an edges spreadsheet. And within your spreadsheet, you need to have, all of your nodes need an ID and a label column. And the edges need a source, target, and type. And the type is either directed or undirected. And I'll show you an example of the data in a minute. And so the edge source, for the edges, the source and the targets, they must use the ID numbers of the nodes. So it's the same principle as NetworkX and Cytoscape in that way. So just before going too much further, I will show you the data that we're going to use for this. In the examples data folder that we've got for today's session, there is Gephi edge list and Gephi node list CSV. And so the node list contains an ID, a label for all the nodes, mean length of stay, median length of stay, and setting attributes. So we've got 2 continuous attributes and a discrete attribute as well. The edge list, we've got the source and the target columns, which are defining the edges using the IDs from the node IDs. Then there is this type column, which is needed, and that just says directed. And then we've got an edge ID, so it's got a unique ID and a weight as well. So once you upload your data, you can go in and you go back to the overview, and there should be a network there for you to work with. Now, the appearance panel is for doing the node and edge formatting, where you can change the color, the shape, size, and text. And you can take these from the attributes which are contained within the data that you've uploaded. They'll pop up as options, or you can do some small analyses, which we'll look at in a moment. So the layout box then down below, this is where you select your node position algorithms. And each algorithm has its own properties, which will pop up in the properties area, this white space below. And you can tweak them and run the layout algorithm. And you can use one or more algorithms in combination, so using one after the other. On the right-hand side of the overview window, we get the network overview, which contains information on different metrics describing the network. So you can run these and it will return values, analyses. So we've got average degree there for the graph, average weighted degree, density, modularity. These are all hopefully things that you'll recognize from NetworkX. Get an average clustering coefficient, eigenvector centrality in there as well. And yeah, they'll allow you to, you can do some limited analyses actually in Gephi itself. When you go to, once you've kind of got the graph looking how you'd like it to look, you can then switch over to the preview panel, the preview window, and do some slightly more detailed formatting on it as well. So in here, you can do things like tweak the node labels, set the font sizes, do the edges, the edge arrows and labels. And yeah, it takes that input from the overview and just allows a bit of refinement. If you do make any changes in here, or if you go back to the overview and make any changes, you'll need to hit the refresh button down in the bottom corner of this window, or else it won't update the view. You've also got down the bottom an export button, which allows you to export the visualization in a few different formats, either SVG, scalable vector graphics, PDF, or PNG format. And you can set up and save some presets of set up these and save them as some style options as well, should you want to. So I forgot to change this slide. That's not good. So what I've given you is we got the Gephi data in there in that example. What I'd like to be able to show you, but I can't, is the data upload process, because when you import a spreadsheet, it is just making sure that you've got everything in the right, that it's picking up on the right columns. I am not going to be able to start Gephi, unfortunately. It's failed on me today. That's one of the reasons I stopped using it. But
Hi, Sean.
yes.
Could one of us open it? I've got it open. You know.
Ah, have you got it? Ah, yes. That's a good idea, Honor. Yes. Yeah, if you're happy to share your screen, and I'll talk through as we just demonstrate the upload process, as I think that will be useful. After that, everything else is playing around. It's just good to be able to get the data in.
I have done a bit of it, but right, okay. So, oh, I've done a bit. Oh, sorry.
That's all right.
Shall I start a new project?
Yeah, that would be good. We'll go through from the beginning.
Don't say it. Yeah. Right. Okay. So tell me what to do.
Great. So the first thing that we're going to do, so we're on the data laboratory window, and we've got on the left-hand side, you can see there's nodes is selected. So the first thing we're going to do is upload the node data. So we go to import spreadsheets, click on that.
Nothing happens. Oh, here we go. Yeah.
And when that gets there, it's having a think, but we select Gephi node list. Yep.
Yeah, here we are. Yep.
And click open. Then it's going through and it's saying, okay, I recognize this as a CSV, comma separated data set. I'm going to import that as the nodes table because it looks like a nodes table to me, and you're trying to import, you're on the nodes bit. So that's great. And then we can go to next. And so here it's just saying that it's picking up on the different columns. So it's got ID, label, mean length of stay, and median length of stay, both of which are double, of type double, which is perfect, and setting, which is of type string, which is just what we want. If those were wrong, you'd be able to correct that at that point. It's picked up wrongly on the data type. And then we can go to finish.
Okay.
And the funny thing is that that isn't finished, because we got one last little job to do here. We can check. So it's picked up, there's 94 nodes there, no edges. And we're going to, instead of creating a new workspace, we're going to append this to our existing workspace. That just means that we don't get loads of workspace tabs opening up. So if we now click OK, and that brings in the node data. Can then go over to the top, over to select edges, and then import spreadsheet again, and we go through the same process with this.
Okay.
And it's just, again, it's picked up, sorry, would you just go back on her? That's it. It's just, the one is just to check each time that you've got it, say, importing as the correct table. So just making sure this time, yep, it's importing it as our edges table, which is great. So it's importing source and target is saying you've got to have those. You've got type of edge, ID, and weight. So we can now select finish. And it's picked up, we've got nodes and edges there. And the main one that we want to do here is make sure again that we select append to existing workspace. and that'll make sure that it comes into the same workspace as our node data. And if we click OK, that will bring in all our data. And now you can go back to the overview tab. And you can begin working on your data. And so I'd encourage, I'll pop everybody back into their breakout rooms. I'd encourage you to, whether you want to work as a group and do it all on one screen, or people want to do it individually and just talk about it as you're going through. You can go through and just have a play with the formatting of the graph. Yeah, you can't really go wrong with these. You can't break these. It's easy to start a new project and come back in. Just noticing Honor is playing with the filters there. It does have some filters that you can put on, so it will subset the graph for you as well if you want to have a go with that. And yeah, so have a play with the partitions, the appearance, because it allows you to choose different attributes on which to partition your the colors in your data and apply colors across the nodes, and have a look at whether it's using partition or ranking. And the other one is if is that, yeah, that gives more of color spline, so you get gradated colors. And that funny looking, because you've got the palette up there, and then the funny looking one next to it does the size as well. It's not a very good representation of size, but it does. So you can do the colors and the size and the text colors and text size as well within that. So lots to have a play about with, lots of buttons to push. I'll put you in your breakout groups to get on with that. Thanks, Honora. Appreciate that.